Hello and welcome to the Notes on Geometric Mean, Part 1. So before we talk about geometric mean, let's talk about the arithmetic mean. No, I'm not pronouncing it incorrectly. It's not arithmetic mean, it's the arithmetic mean. There is another name for arithmetic mean that I'm sure you've heard of in the past, and that is average. So an arithmetic mean is just finding an average. Okay, in stats we just call it a mean. How do you find the arithmetic mean between 18 and 12? If I wanted to find the average of those two numbers, I would add them together, so 18 plus 12, and then because there's two numbers, I would divide by 2, and this would give me 30 over 2, aka 15. If there was 3 numbers I was finding the arithmetic mean between, I would add all 3, divide by 3. If there were 70 numbers, I would add all 70, divide by the 70. So you just divide by the number of numbers that you have. The geometric mean is something that you probably haven't seen before. And what it is the geometric mean between two numbers, a and b, so a and b would be two numeric values, is the number x that would solve either a, the following proportion, a over x is going to equal x over b, or if you solved for x, you would get x equals the square root of a times b. And the reason this is true is if I was to take this one and cross multiply, I'd get x squared equals a times b. To get x by itself, I would have to square root the left side, which would mean that I have to square root the right side, so it'd be the square root of a times b. Important to note here, the geometric mean between two numbers is the number x. So here, this is the geometric mean, and so is this x. So that's the thing that would appear twice if you were to write a proportion, which is going to become important when we do these problems with triangles in this section. The first example here is showing that I wouldn't necessarily do the proportion. I would just say if x is the geometric mean and they give me two numbers, I'm just going to say x is the square root of 32 times 8, and so I would get x equals the square root of 256, and so that happens to be a perfect square. It is 16. It's not always going to be a perfect square, but you're always going to want to simplify it. So if you ended up with something like square root of 80, you want to simplify that number by finding the perfect square factor and simplifying it that way. This next example is a little bit different. Here we're given the geometric mean. So square root of 84, is the geometric mean between 7 and what number? So if 84 is the geometric mean, the way I like to explain it to students is this is the number that will appear twice in the proportion. And it's going to be across from each other along the diagonal. Sorry, this is... All right, so if I was to write a proportion, if square root of 84 is the geometric mean, that means it's going to appear twice and across from each other. Now, how did I know to write it there? I didn't. I could have also written it this way, where the square root of 84 appears in the first denominator, second numerator, or like I had previous, the first numerator, second denominator. All right, so it is the geometric mean between 7 and what number? So I would put 7 in one of the empty spots, and then let's say x or a. Let's maybe put a so you don't think it's the same x. So let's say 7 and a, or if I put it here, I could do a and 7, whatever. Anyway, it's fine. I'm going to cross multiply. A times 7 is 7a equals the square root of 84 times the square root of 84. When you take a square root and multiply it with itself, you're releasing it from its captivity or whatever. So 84 would just be released. Divide both sides by 7, and a is going to end up equaling 12. So yeah, just remember that if you take a radical and multiply it by itself, like if I had square root of 3 times square root of 3, that is going to equal just 3. Same thing with rationalizing the denominator. If I had 5 divided by square root of 2, I would multiply top and bottom. The reason I multiply by square root of 2 over square root of 2 is because I release the 2 from the denominator. It would just be 5 root 2 over 2. Let's talk about altitude to the hypotenuse theorems. If the altitude is drawn to the hypotenuse of a right triangle, so in this picture, the altitude would be from angle C down to D, it's going to divide the triangle into 3 similar triangles. So we have our original one, triangle ACB, and we're going to figure out which 2 triangles it is congruent to. So I have a yellow triangle and a green triangle. What I'm going to do is redraw them so that they're all facing the same direction. So I'm going to redraw the yellow triangle and I'm going to redraw the green one. So let's go ahead and do that. So when I redraw the yellow, I'm going to make it look and face the same direction as the big ACB. And then I'm going to draw the green one. The green one's smaller, so I'm also going to make it, draw it this way. So this one had a right triangle up in the corner, so I'm going to put my right angle here, and I'm going to put my right angle here. Now, another thing that I would do is I like to mark the angle. I'm going to put 1 arc there, so that would be 1 arc here, 1 arc there. And then here, let's put the double arc. So double arc and double arc. Whoops. Let's look at these 2 triangles and now try to fill in their letters. So the yellow triangle has vertices A, D, and C. So I'm going to use these angle markings to figure out which angle corresponds to what. So the first thing I notice is here, angle A has the 1 arc. So that means I'm going to put A right there. The right angle in the yellow triangle is D. And so then by process of elimination, it has to be C that's the last vertex. Okay, let's look at the green triangle. The green triangle has a double arc of B, so I will put B where there's a double arc. The right angle also appears at D, and so then by process of elimination for this green triangle, if the 3 vertices are C, D, and B, and I already have D and B, I will put a C right here. And so now that I've redrawn them, all 3, that they have the same, they're facing the same direction, I will pay attention to how this first triangle was written, right? It says A, C, B. A to C to B. So bottom left to the right angle to the bottom right. So I'm going to follow that same direction here. So it's going to be A, D, C. And then I'm going to follow that same direction for the little green triangle. Bottom left to the right angle to the bottom right. So C, D, B. We will practice this a little bit more. I'm going to draw one in class and have it initially facing a different direction so that you could practice this, because I know this is a little bit challenging for some kids. So what those 3 triangle similarities bring us to is the altitude to hypotenuse theorems. The altitude to the hypotenuse, so in our case CD, is the geometric mean. So if it's the geometric mean, it means it appears twice in our proportion. And now what it's going to become is the geometric mean of the 2 chunks. So imagine that this triangle, ACB, was just hanging out, minding its own business. All of a sudden, CD came in and got dropped and kind of split up the hypotenuse. The hypotenuse gets split into what we call chunks, right, or pieces. But here's a chunk, there's a chunk, everywhere, chunk, chunk. JK. Okay, so it becomes the geometric mean of those 2 pieces. So AD is one of them, right here, and the other piece is DB, right there. The other theorem that comes from this is the leg of the right triangle. So imagine the initial right triangle, ACB. The legs become the geometric mean of the chunk of the hypotenuse that's next to that leg, and then the entire hypotenuse. So if I'm looking at CB as my original leg, it's the geometric mean, so it's going to appear twice, diagonal from each other, of the entire hypotenuse, which is AB, that's what goes here, and the piece of the hypotenuse, the chunk that's next to that leg. So if I'm looking at leg BC, the chunk next to it is DB. But a triangle has 2 right legs, right? This is also a leg. So it's the geometric mean, AC, of the entire hypotenuse, so again, AB, and then the chunk next to this leg. So this chunk is next to this leg. DB, that chunk is next to that leg, adjacent to it. So this case, we would do AD. I'm going to go back and try to recolor this a little bit better. I'm going to color the entire chunk here. I'm going to color it this dark gray color. I'm going to color AD. Nope, don't want to use red. I already used red. Let's do green for this chunk, and then yellow for this one. So the ABs, notice I kept them dark, but here DB is my green one, and then AD is the chunk next to the blue leg. Okay? Hopefully that maybe clarifies it a little bit. I hope it does. All right, so here's my tiny little notes. Okay, so here's a review of the theorems. You could have this, like I know a lot of you like to somehow cut and paste this into your notability when you're working on these, but for the leg, the geometric mean, so either leg, it's going to be the entire hypotenuse, whole hypotenuse, and then the part that's adjacent to it. So if I was looking at this leg, this is the part next to it, and if I'm looking at this leg, this is the part next to it. So it just depends. You have to change it. Then when you have the altitude, so here's the altitude, it's the geometric mean, so it appears twice across from each other of the two parts. So one of my parts here is red, the other part I colored yellow. Okay, so that blue segment created those two parts. It's the geometric mean of those two parts. All right, let's decide which proportion would be appropriate to use, and then we're going to use it to solve for x. Well, you're not always missing the thing that is the geometric mean, but when I look at this problem, I don't even have the legs of the triangle. So I know that I'm definitely not going to use a leg theorem because I don't have legs. So I am going to use the altitude. So the altitude is the geometric mean, so that means it's going to appear twice across from each other of the two pieces, 3 and 4. Those are the two chunks that got created by this altitude. Cross multiply, you get x squared equals 12. X is going to equal the square root of 12, which I can simplify to be 2 square roots of 3, because 12 is the square root of 4 times the square root of 3. The square root of 4 is 2. Okay, the next one, are we going to use the leg proportion or altitude? Looking at this picture, because I have a leg value, I'm going to use the leg proportion. And there are going to be ones that we're going to do, especially the next lesson, where you're going to have to do both. So it's not like one or the other. These are the easier of the lessons. Okay, so the leg is the geometric mean, so it's going to appear twice of the entire hypotenuse, so 15 times the piece next to this leg. So because I'm looking at x, I'm going to take the piece next to x and call it 5. X squared is going to equal, sorry, I don't know what that, sorry, I just had some weird things pop up. I have no idea what just happened. So here, when I cross multiply, I'm going to get x squared equals 5 times 15 is 75. Keeps jumping for some reason. Okay, so x is going to equal the square root of 75. Square root of 75 is the square root of 25 times 3. Square root of 25 is 5 root 3, right? I could think like a little think bubble here. Well, I don't like the way that looks. But like square root of 75 is equal to the square root of 25 times the square root of 3. Square root of 25 is 5 square roots of 3. All right, let's decide which one we're going to use here. I see that I'm not even given the legs of the right triangle, so it's not going to be a leg theorem. It's got to be altitude. Okay, so the altitude is the geometric mean. That means it appears twice across from each other of the two pieces of the hypotenuse. So I have this piece is 5, but I don't have this piece. So as before, when you're given the entire thing and a piece of it, the way we find the missing piece is the whole thing, x minus 5. Okay, so now I cross multiply. I'm going to have 5 times x minus 5 equals 64. I'm going to distribute on the left side. 5x minus 25 equals 64. add 25 to both sides, I'm going to get 5x equals 89. Dividing by 5 will give me x equals 89 fifths. Okay, last one here. We are going to find x using legs or altitudes. This one's going to be a leg one. I don't even have the altitude here, so why would I use an altitude? So the leg is the geometric mean of the piece of the hypotenuse next to it. So if I'm looking at 4, this is the piece next to it, x, and then the entire hypotenuse. So if the two pieces are x and 6, together they would be x plus 6. All right, so let's cross multiply. We're going to have x times x plus 6, and that is going to equal 4 times 4, aka 16. Let's distribute. Oh, there's some weird things down here. Oh, well. X squared plus 6x is going to equal 16. We want this to equal 0, so x squared plus 6x, I would subtract 16 from both sides. And now I'm looking for two numbers that multiply to be negative 16, and at the same time, they're going to add up to 6. They are 8 and negative 2. So x would equal negative 8 or positive 2. Now looking back at my picture, I have to make sure that both of these x values are fine. Notice that x is this piece of the triangle. How can that possibly be a negative answer? It cannot, so we only have one answer. Even though we algebraically get 2, we only have 1. All right, what do you call more than one L? A parallel. All right, so you will be working on day 8 classwork the next time you're in class. Thank you so much for watching. Have a good one. Bye.